Okay, well, so we see how we can use the log mean temperature difference method to select a heat exchanger. What if we already have a heat exchanger and we want to say, okay, if I put this heat exchanger in, run these two fluids through it, what will the exiting temperatures be? How do we do that? Well, remember, for the log mean temperature difference method, we need the approach temperatures at either end of the heat exchanger. If we don't have the temperatures of the exit, we don't have, at most we might have one approach temperature if we're talking about a parallel heat exchanger, but in a counterflow heat exchanger we don't have either of the approach temperatures. So what do we do there? Well, we're stuck, aren't we? There's no way that we can calculate the log mean temperature difference. So what do we do instead? Well, you could guess, right? You could guess and check. And there are intelligent ways of doing it. For example, energy is conserved, so if one stream, you guess an exiting temperature for one stream, calculate the heat transfer rate in that stream, and then realize it has to be the same heat transfer rate into the other stream, calculate exiting temperature and go from there, and see if the area you calculate matches the area that is present in the actual heat exchanger. But that's an iterative process. We don't like those. We'd like some better way of doing this. Well, there's the effectiveness number of transfer units method. It's developed essentially by London, and there was another name. I think I've got it here in just a second. But basically he published something in 1980, but he wrote it in 1942. And if I remember right, it wasn't him that actually published it. Someone else published it. I don't remember for sure. It doesn't matter, but I wanted to give tribute to the person that is responsible for this. And it's a generalized method, as he said, for heat exchanger analysis. Now, most of these ideas were actually in the literature, but they weren't taught and they weren't used in industry. Kayes, that was the other name, London and Kayes. I believe that Kayes had a lot to do with the publishing of this. They both, in any case, published a book, Compact Heat Exchangers, which is sort of the go-to Bible, if you will, for heat exchangers. I'm not going to show you how this method was derived. I'm not sure that I know how it was derived, but I will show you how to use it. Here's the important part. We need to have a couple of definitions. First of all, there's something called the effectiveness of the heat exchanger. And the effectiveness is the actual heat transfer rate that the heat exchanger produces divided by the maximum theoretical heat transfer rate that you could have with the fluids you have available. So the maximum heat transfer rate is based on the maximum temperature difference of the two fluids. So if you look, delta T max is equal to the temperature of the hot stream in minus the temperature of the cold stream in. That's the maximum driving force for heat transfer, right? That's the biggest difference in temperature anywhere around the entire heat exchanger. And then the maximum heat transfer rate is equal to the minimum capacity rate. Remember, mass flow rate times heat capacity. There's two of them, one on the hot side and one on the cold side. Whichever one's smaller is the one we plug in here, multiplied by the maximum temperature difference. Now you might look at this and say, wait a second. Q dot max equals minimum capacity rate. What is that again? Oh yeah, that's the mass flow rate times the heat capacity. And I can see that one would be larger on the hot side than on the cold side, or vice versa. So I can see one's going to be bigger and the other one's going to be smaller. But it seems strange to use the maximum temperature difference in the fluids and the minimum capacity rate. Why would we put those together? Why wouldn't we use the maximum capacity rate? Well, the reason is because the capacity rates really indicate which fluid is limiting the heat transfer. See, one of the fluids caps the heat transfer rate. It prevents the heat transfer rate from going above a certain amount. It's kind of like if you're driving with your foot on the brake, right? The brake limits how fast your car can go. In that sense, the minimum capacity rate side is the one that limits, and there's no way to get past that limit and get a higher heat transfer rate. So this is the way that the maximum heat transfer rate is defined for this procedure. If you're okay with that, we'll just use it as that. That's just the way it's defined. But there is a reason for using the minimum capacity rate with the maximum temperature difference, even though that seems odd. Anyway, remember the capacity rates are, we've got the capacity rate on the hot side, capacity rate on the cold side. They're the mass flow rate on the hot side times the heat capacity on the cold side, and the mass flow rate on the cold side times the heat capacity on the cold side, right? Between those two, as I said, one's going to be bigger than the other, so that defines for us whichever one is the minimum capacity rate, C sub min, okay? we have to calculate both capacity rates, and remember we'll be able to. We know how much mass of the two fluids we want to have flow through. We know the physical properties of these fluids, or we can go measure them. So coming up with the minimum and maximum capacity rates are fairly straightforward. Now the way that the effectiveness is actually used is to calculate the actual heat transfer rate from the effectiveness multiplied by the theoretical maximum heat transfer rate. And so since the maximum heat transfer rate is C sub minimum times the maximum difference, which is the two input temperature differences, which by the way, realize we always know that, right? We're trying to figure out the exiting temperatures, not the entering temperatures, regardless of whether this is counterflow or co-current flow. Since we always know this, if we could get the effectiveness, we could get the actual heat transfer rate. Well, that sounds good, but it sounds like more of a transfer of ignorance than anything, right? I mean, I can see how we could get C maximum, C sub minimum. I understand we know the incoming temperatures of the two streams. That makes perfect sense. Where the heck is this effectiveness going to come from? From equations that have been derived for different geometries of heat exchangers. Where do these derivations come from? I'll refer you to London and Kay's if you want to see all of that. We're just going to use them. So this is a page in your book. You should find it. I think I've got a page number for you in just a minute. But these are the equations, and depending on what geometry of heat exchanger you have, you select the particular type and then you use the appropriate equation with something called the number of transfer units and the ratio of the capacity rates. Now I know this is getting confusing. Now we got 5 different C's running around. We've got the heat capacity on the cold side, we've got the heat capacity on the hot side, we've got the minimum capacity rate, which combines the heat capacity with the mass flow rate. We got the capacity rate on the other side, right? One of them's maximum and one of them's minimum. You could argue we've got 7 C's running around. And now we're using C again to represent the ratio of the two capacity rates, where we always take C minimum over C maximum. Sorry, I didn't make up the symbols, but fortunately, actually, this capacity rate is one of the easier things to get at. Okay, so coming up with a capacity rate really is not that hard. You just have to keep all the C's straight, that's all. The number of transfer units sounds like something theoretical and difficult to use, but it's actually not too bad. Remember, if we already have a heat exchanger, we know its surface area, and we should be able to get at its overall heat transfer coefficient, U. Now don't worry, I'm not going to make you calculate U unless, you know, just from geometry or what the material's made of or anything, unless I've given you everything else where you can calculate U, okay? But most of the time I don't make that an unknown. I just give you, I say here's a heat exchanger, its UA product is this number, now let's go use it. So UA is something you're essentially given because you're told exactly what heat exchanger you're working with, right? You've got a heat exchanger already in existence. Theoretically you could find its UA product without too much trouble. So the number of transfer units is defined as the UA product divided by the minimum capacity rate, whichever one that turns out to be, the hot side or the cold side again. So if this is the case, then you can calculate the effectiveness using the capacity ratio, capital C, and the number of transfer units in these equations. Now I have helped you out a little bit. I've been very kind to you. I've actually programmed all of these equations into a spreadsheet for you. And so if you look in the learning module, you'll find it, you can download them, and you're welcome to use them. It's really easy to make a mistake with these equations when you're punching it into a hand calculator. If you want to put these into a graphing calculator, you're welcome to. You can use the spreadsheet on tests. I have no problem with that. These are just equations we want to calculate. However, your book does have a mistake. There are 2 errors on page 729. I have scanned that page, I have corrected those errors and put them here. I know for the both fluids unmixed, the cross-flow heat exchanger there, or one of them, they missed a square bracket after the 1, and it makes the equation somewhat ambiguous. You can't tell where there's supposed to be a square bracket before or after subtracting the 1. So it turns out it's supposed to be after the 1. Also, I believe there's a mistake where there's either a positive sign or the 1 is missing or something in the equation right above this. It's right in my slides. Make sure that your book matches all of these. And your book may have another printing error in this. I don't know. So double check all of them and make sure they match. Now I have programmed the correct equations into the spreadsheet. Here's a little bit better version of the same table from another textbook. So I put this into the slides for your reference. It looks a little more complicated, it seems a little more complicated to use, but it's the same thing. So there's the reference. and Kropra, I think is how you say it, DeWitt, Bergman, and Levine. It's a very famous heat transfer text. So most schools use this. The reason I use single for this class is because I need a combination of heat transfer and thermodynamics, and I don't want to make you buy two books. Now, the effectiveness number of transfer units, you can see that those equations can be a little bit difficult. It turns out there are also charts for these instead of the equations. So the equations have been plotted, and what you can do is look up the number of transfer units on the x-axis, go to the appropriate capacity ratio line, that's what each of these lines are, and then read off the effectiveness. Now, if you're doing this by hand and not using the spreadsheet, it's really good to go to these charts first, figure out about how much effectiveness you should get from the equations, and that way once you get a more precise number, hopefully from the equations, you got a sanity check to make sure that you haven't, just fat-fingered the wrong button on your calculator. Now you can work this the other way, it turns out. You could go from an effectiveness to a capacity ratio down to a number of transfer units. Why would that be useful? Well, because if you think about it, you can work this backwards. Really, the number of transfer units is related to the size of the heat exchanger. Thus the name number of transfer units. So could we work this backwards where we say, okay, I'd like to size a heat exchanger. I know what entering and exiting temperatures I want. I know what mass flow rates I need. I know what fluids I've got. So how big of a heat exchanger do I need? Well, think about it. If you know the fluids that are flowing, you can calculate the capacity rates for both sides, right? You can figure out which one's max, which one's minimum. That means you can get the capacity ratio C. You can also actually calculate the heat transfer rate that you desire, right? Because if you know the entering and exiting temperature of a stream, you know the flow rate through the hot side or the cold side, you can calculate the rate of heat transfer. You can also calculate the maximum theoretical rate of heat transfer, Q dot max, because you know both the hot stream and cold stream maximum temperatures around the heat exchanger, and you know the minimum capacity rate. So getting Q dot max is easy. Now getting the actual heat transfer rate over Q dot max is easy, and now you've got effectiveness, right? Because you just take the ratio of those two. That is effectiveness. So if you've got C, the capacity ratio, and you've got effectiveness, you can plug those into the equations, basically the inverse of the equations I just showed you, and calculate the number of transfer units, which gives you the UA product, which is exactly what the log mean temperature difference method gave you before. So what I'd like you to do is find this table in your book as well, put a tab there as well as the last one, and on it I want you to write either competition for the LMTD method or use this for size in a heat exchanger. The last equations I showed you, that last set where we had to correct some of them, on it you should write use for predicting the performance of a heat exchanger. Okay? So this can be used in lieu of the log mean temperature difference method. And I have also programmed these into a separate tab in that same spreadsheet. So you've already got all of this if you just download that spreadsheet. I'm being really nice to you. Here's the similar table from the other text that I referenced for you to look through. Notice the symbols are a little bit different. These authors use C sub R for the capacity ratio. I think that's probably a good idea. Unfortunately, our author does not.